Good day, grade 12. Today we are going to look at a National Senior Certificate Exam, November 2025. It's chemistry, paper 2. The next page is our instructions. Then we are going to quickly proceed to our multiple choice questions there, which is our question number 1, right? So 1.1 reads there. Which one of the following homologous series contains a hydroxyl group that is bonded to a saturated carbon atom, right? So by saturated there, we're referring to single bonds between carbon to carbon atom. So option number 1 says it's a ketone there. So a ketone, according to this, is looks like this. A ketone, we're going to have a C double bond C there. So this is the functional group of ketones. So it means this one is going to be incorrect, because for a hydroxyl group we're looking for an OH group. Then aldehydes, they're almost similar to our ketones, where we are going to have our hydrogen, then that is bonded to this oxygen, and then like that, and then carbon like that. This is our chain. Then when it comes to alcohols there, what are you going to have? You're going to have an HC, then there an OH at the end, with the rest being what? Your hydrogens there. So it means the OH group, that's what we are looking for, that is referred to as our hydroxyl group. So it means our correct option is going to be option C. Then moving on to 1.2 says the compound. Consider the compound shown below, right? So we're looking for the correct IUPAC name of the above compound. So if we're to look at this functional group there, we can see this one is an aldehyde, right? So this is the functional group of aldehydes. Then in terms of our numbering here, we're supposed to number to the sides closest to the functional group. So it means here I'm going to start numbering my carbons as carbon number 1, 2, 3, 4, and 5 in order to get the longest chain, right? So for us to get the longest chain, our longest chain there is going to be 5 carbons. So if we're having 5 carbons, then it means here we're going to have what we refer to as what pent as the longest chain for our parent name. Then in terms of this, we can also see that in carbon number 2, we also have a side chain or a substituent, which is a methyl, right? So it means here we're going to say 2-methyl. So it means on carbon number 2, we're having a methyl. So option A is already out, and option 4 is already out because this methyl is not on carbon number 4. Then we're left with option B and C. So according to this, we can see our longest chain, we said, is going to be pent, and then this one is having like ethyl there. So B is already incorrect. So our correct option is going to be option C, which is 2-methyl pentanal. Then 1.3 is there. Consider the reaction. We're having a reaction CH3H6 and then Cl2 to give us a C3H6Cl2 there, right? So then they're saying the name of the reaction is, so according to this, what are we adding there? We're adding a chlorine, which is our Cl2, and then it falls under halogens, which is group number 7. So it means here, what are we doing? The name of the reaction or the type of the reaction there is going to be referred to as halogenation. So A, C, and D are going to be incorrect. Then moving forward to question 1.4 is there. Consider the vapor pressure. Consider the vapor pressure against temperature for the caves for the 3 chain isomers under standard atmospheric pressure. Then here they are saying consider the statements regarding the curves of the 3 isomers, right? So we've got our A, B, and C. So according to our analysis there, option number 1 there, item 1 says a compound A has the shortest chain length. So option 1 says here it has got the shortest chain length. Yes, so here we can see A is going to have a shortest chain length. So how do we conclude that A has got the shortest chain length? Because here, if you look at the high vapor pressure, there is going to have the highest vapor pressure. So in terms of our vapor pressure, we know that whenever we're having a high vapor pressure, we're going to have a low boiling point, and low boiling point is usually associated with what? The lowest, shortest what? Chain. So it means our option 1 there is the correct. Then option 2 says the boiling point of compound B is T2, right? So we can see the T2 there for compound B. Here there is no more change in terms of the temperature. Therefore, we're going to say option 2 is also going to be correct. Then option 3 says compound C is at a gaseous phase at T2. Compound C is at a gaseous phase at T2, which is incorrect. So it means our options that are correct is 1 and 2. Then says which of the statements is or are true. So 1 and 2 only. So our option A there is going to be the correct option. Then moving on to 1.5 says they consider the synthesis reaction of ammonia, which is your NH3. So we're having N2 gas, then 3H2 gas also to give a reversible reaction of what? NH3 gas there. Then they're saying the rate at which N2 gas is consumed during the reaction is X, right? mole per dm cube per second, like that. Then which one of the following is the rate at which ammonia NH3 is produced in mole dm cubed per second with respect to N2? So it's a matter of us comparing this N2 versus 2 NH3, right? So in terms of our mole ratio, we can see the ratio is 1 is to 2. Then in terms of our X here, we can see here we're having an X. So this side, it means we're going to have a double, right? So in terms of this, we're going to multiply 2 by X, therefore getting a value of what? Of 2X. So in terms of this, it means our option B is going to be the correct answer there. So we consider the mole ratio. Again to this here, if you look at the coefficients there, is 1 is to 2 there. Then moving on to 1.6 says here, consider the following reaction at equilibrium. So the reaction is at equilibrium, therefore we're having COCl4 2 negative arc plus 6H2O, which is a liquid, to give us CO H2O, then 6 2 plus, then arc also 4Cl negative arc, right? So the solution is currently pink, so they gave us a color which is pink. Then after that, they are saying concentrated hydrochloric acid HCl is added to the equilibrium mixture. So it's a concentrated HCl that is added to the equilibrium mixture. Then which one of the following combination correctly describe the effect that the addition of concentrated hydrochloric acid HCl we have on the equilibrium constant Kc and the color change of the solution, right? So now in terms of Kc is only affected by a change in what? In temperature. Temperature is the one that affects Kc. So it means here we're looking at two scenarios here: increase and decrease. They're going to be incorrect there. So there is no increasing and decreasing, but in terms of our Kc, we know there is no effect there. Then in terms of a color change there, it means our solution is going to turn from pink to blue there. So our option B is going to be the correct answer. Then moving on there to 1.7 says, which one of the following substances can be classified as a Lowry-Bronsted acid? Remember, this is an acid, is a proton donor. So according to the list here, C is the one that can act as a proton donor. So it's going to be 1.7, it's going to be option C. All these there can act as what? As bases there. Then moving on there to 1.8 says, consider the salt. They were given salt CH3COONA. Then it says here, which one of the following combination correctly identify the hydrolysis reaction at and the pH of the salt, right? So in terms of our pH there, we should know that the pH of a salt there is going to be greater than 7, right? So we're going to have our option A as well as option C there. So B and D, they are incorrect. Then in terms of the other one there, what do we also know there? We know also that our CH3 is going to be formulated in such a way that is going to formulate a product which is a COOH, like that, right? So we're going to have a product which is COOH, more of our a carboxylic acid. So it means our option A is going to be the correct option there. Then moving up forward there, what we're looking for is 1.9. It says here, consider the cell notation of a galvanic cell below. Then which one of the following reaction occurs at the cathode, right? So now we know that according to our analysis there, here we're going to have our anode. Then on this other end here, this is where we are going to have our cathode, right? So the PT there is more of like inert, right? So this one is inert, right? So it's unreactive there. So usually it's used for as a conductor there. Then after that, now we also need to know that here at the anode there is an ox, right? So it means oxidation occurs here. Here we are going to experience oxidation. Then on this other end here, we are going to experience what? Reduction, right? So having that information now, this says which one of the following reactions occurs at the cathode. So we're focusing mainly on MnO4 to Mn2, right? So in terms of this here, what you're going to do is that we start maybe with MnO4 to formulating what we refer to as what? An Mn2 plus, right? So Mn2 plus, like that, right? So this reaction here from there to there is going to represent what we refer to as what? A reduction, right? So it's going to be reduced. MnO4 is going to be reduced, right? So in terms of this, if it's reduced, then now we also need to know how this is going to affect the whole equation as a whole, right? So in terms of this, automatically we can see here they said at the cathode. So we have identified our cathode. So it means option C and D are already out. They are incorrect, right? So now we're left with option A and B, right? So now to consider option A and B, we're supposed to say Mn is Mn in Mn4. So I'm going to just like maybe go through the redox reactions and all. So allow me maybe to use a blank page there. So I'm going to say our Mn there. So Mn in MnO4 negative, right? Here's got an oxidation number, is an oxidation number. I'm going to say hash of what? Of 7, right? So having an oxidation number of what? Of 7 there. So, oh, by the way, it should be positive 7. Then Mn2 plus, right, has an oxidation number of what? Here's an hash of what? Of 2, right? So I'm going to say of positive 2 like that. So having this information, so we know that it actually gains electrons, right? There is a gain in terms of what? Of electrons, right? So this gains electrons, so it's going to be what? To be reduced, right? So in terms of our equation, we're going to say your MnO4 negative there plus 5 electrons. So 5 electrons to give us Mn2 plus, right? So we can see here we started with an Mn. So now we're having a 7 there, positive 7 from what? To from Mn2 plus to a positive 7 there, right? So there we now know how many electrons have been gained there, right? So it means now if we were to balance the equation, we're supposed to balance with the oxygen using our H2O, right? So now in terms of this, we're going to say your Mn O4 negative is oxygen, so it means it has got 4 oxygen, has 4 oxygens like that, right? So now in terms of this atom, while Mn on this other end, I can say Mn has got how many? Has none, right? So it has got none on the other end, None, it has got none. So now we need to know that for us to balance, we need to add the water on the side of the what? Of the Mn there, right? So we need to add the water on the side of the Mn, right? So we're going to add our H2O. So if we add our H2O, what is going to happen there? We're going to add to the Mn to the right hand side of this one there, right? So it means now we're going to have something like that looks now like this. MnO4 minus then plus 5 electrons, then to give us an arrow there, I'm going to say Mn2 plus, then plus 4H2O, so as to balance what? The oxygens there. Then now we have 8 hydrogens, so you can see here on this other end now we're having our 8 hydrogens on our right. So what does that mean? So to balance we should add also H plus 8 there on this other end. So our answer there is going to be our MnO4 negative, then plus 8 hydrogens, which is H plus, and then plus 5 electrons there, and then to give us a value of what? Mn2 plus, Mn2 plus, and then plus 4H2O. So this is how we balance our equation there. So if we are to look at this and then to compare with this one at the top there, we'll see that the correct option there that we are going to have is option B. Then moving on to 1.10 there, it says a spoon is plated with silver He during the process of what? Electrolysis, right? Then which one of the following graphs best describe the concentration of the silver ions He in an electrolyte over time, right? So He is going to remain what? Constant there. So if it remains constant there, concentration there over time, it means our answer, our correct option there is going to be option B there, right? So according to this, you can see the concentration remained at constant throughout then. Then now moving on to structured question there, we have got question 2, which is consider the organic compounds A to E below, then says we're having A until E like that, right? So it says define functional group, right? So here I'm going to say a functional group there, I'm going to say is a bond, right? So it's defined as a bond. So I'm going to say a bond or an atom or an atom or atoms, group of atoms like that, that determine the physical and chemical properties of a group of organic compounds, of organic compounds. like that. So this is how we define our functional group. Then 2.2 says that write down the letter of a compound that contains a carboxyl group, right? So we're looking for a carboxyl group there. So a carboxyl group there, if we were to look at this one there, we're going to have our option 2.21. They were going to have an option of what E there, right? So a carboxyl group, right? So from a carboxylic what acid, which is our COOH there, right? So it means there we're going to have our option E. Then here's the general formula of CnH2n. Oh, right. So a single oxygen there. So as a clue there, you can see which one has got a single oxygen there. You can see here is a butanone, which is more of what a 3-methyl butanone there is a ketone, right? So that's what we're having there, which is our option A, right? Then we move on to here's an empirical formula of what CH2. So here's an empirical formula of CH2. So according to this, there here this one there is no answer because we are not given such in terms of our table there, right? So in terms of our organic compounds A to E. Then after that, I'm going to proceed to 2.3 says how will the molecular mass of E compare to ethyl methanoids, right? Then after that, they're asking us to choose greater than, smaller than, or equal to, and then we're supposed to give an answer there, right? So the correct answer there is going to be equal to, right? So equal to, so our answer is equal to. So the reason behind is that compound E and ethyl methyl are functional isomers, right? So the two, I'm going to say they are functional isomers, right? So this is the reason behind why they are equal to, right? So now it says here, write down the 2.4.1, the structural formula of compound A, right? So if we were to look at compound A, there is 3-methyl butanone, right? So it means here what we know is a ketone, right? And then the but there refers to 4 carbons in terms of that, right? So I'm going to write this one there, right? The structural formula of compound A, I'm going to have the longest chain as having 4 carbons, 2, 3, 4 for but. Then after that, what else do we have there? I'm going to say 3-methyl butanone, right? So it's 3-methyl butanone. So we also know that on carbon number 3, we're going to have what? A methyl group, right? So if I'm to count from right to left, I'm going to say 1, 2, 3. Or if I'm to count from right to left, it's going to be 1, 2, 3. So it means now I can also put my carbon there at the bottom there so that it formulates a methyl, right? So it's going to be a hydrogen, hydrogen. Then at the top also hydrogen. Then the rest there is going to be our hydrogens, right? Then after that now, we need to formulate a ketone, right? So in terms of this, I'm going to put a double bond on this other carbon then after that, remember each carbon bonds are many times 4 times, right? So hydrogen, 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 like that. So this is how we are supposed to write the structural formula of what? Of 3-methyl butanone, right? So you can see the functional group there is also present there to show that this is a ketone there, right? Then moving on to 1.2.2, 2.4.2, it says the IPEC name of compound E. So we're looking at E there, right? So in terms of our E there, we can see this is it falls under carboxylic acid, right? So in terms of our carbons there, we have 1, 2, 3. So the longest chain there is 3 carbons, so it's propanoic acid. So this one is going to be referred to as propanoic acid. So IPEC name of compound E is propanoic acid, like that. Then moving on to our 2.4.3 is there. 2.4.3 says the IUPAC name of compound D. So we're looking also for the IPAC name of compound D. So if we're to look at this one there, we are going to have a triple bond. We can see there's a triple bond, so formulating an alkyne, right? So in terms of this, we are supposed to count the number of carbons, right? So if I'm to write from left to right, it's going to be 1, 2, 3, 4, then 5 and 6, right? So it means now we're going to have the longest chain as being how many carbons? 6 carbons, right? So in terms of this here, so this is how we're supposed to number. Remember, if I'm to number from this one, 1, 2, 3, 4, 5, it means the functional group is going to be very far, right? So in terms of this now, if I'm to look at the chain there. The triple bond is going to be on carbon number 2, right? So on carbon number 4, it means we are having a substituent or a side chain. So I'm going to start with that one there. I'm going to say this is 4-methyl. So if we're having a methyl, 4-methyl, then after that now, the longest chain is 6 carbons. If it's 6 carbons, so it means it's a hex, right? So I'm going to say hex. Then where do we find this triple bond to make it? So it's on carbon number 2. So in terms of this, it's easier if you count the first bond 1, and then the second bond is going to be 2. So you're going to say 2 dash, then the suffix for alkynes is going to be what? YNE. So that's how we write the IUPAC name of compound D. Then moving on to 2.5 says compound B is a secondary haloalkane, right? So compound B is compound B. So we're having this one there as being what? A secondary haloalkane, right? So then after that, draw the structural formula of compound B. So we're looking for the structural formula of compound B, right? So there, I'm going to draw it at the top there. So it means now we're having how many carbons according to this? We're having 3 carbons, 1, carbon number 2, and carbon number 3, right? So now to formulate a secondary haloalkane, so it means now my chlorine there, which is my Cl, is supposed to be bonded to this carbon, and this carbon here should be bonded to, other carbons, to 2 other carbons, which are going to be these ones. Then after that now, I'm going to add the hydrogens, because remember your carbon should always bond 4 times like that. So it's going to be H and H there, and at the top an H, and then another one there and H. So that's how we draw the structure of what, write down the structural formula of what, of compound B there, right? So moving on to 2.6 says there, using the molecular formula, write down the balanced equation for the complete combustion of what, of compound D, right? So in terms of this, we should know whenever we're talking about complete combustion there, our product should always be carbon dioxide, what, plus water. So these are our products for complete combustion there. So whenever they say complete combustion, carbon dioxide and water. When it's incomplete, we are going to have what, carbon monoxide. So we're focusing on compound D there, which is 1, 2. It has got 2 carbons. So I'm going to say how many carbons do we have there? For compound, they said compound what, B or D? Oh, we're referring to D, right? So in terms of D there, so we need also to go back and now count the number of carbons that we have. I'm having 1, 2, 3, 4, 5, 6, and a 7, right? So it means I'm having 7 carbons. Therefore, I'm going to say C7. Then after that, also I'm supposed to count the number of hydrogens on this one there. So it means here I'm going to have the first hydrogen 1, 2, 3. Plus 3 is 6, 7, plus 3 is 10, 11, 12. So I'm going to have 12 hydrogens there. So it's going to be C7, then H12 there, H12 like that. Then now for it to combust there must be the presence of what? Of oxygen, benzene, excess of what? Of oxygen, right? So remember I said the products are always going to be carbon dioxide plus what? Plus your water there for complete combustion. Then after this now, we're supposed to balance the number of what? Carbons, hydrogens, and oxygens, right? We can see on our left-hand side, we're having 7 carbons. Then on our right, we're only having 1, right? So for me to balance, I'm going to put a coefficient of 7 there. Then after that now, it means this 7 also affects the number of what? Of carbons, right? So as a rule of thumb, we should start with carbons, then followed by hydrogens, then the last part is going to be oxygen. So we balance them in this manner. Carbons first, hydrogen second, then lastly, our oxygens, right? So moving on to our hydrogens there. So we can see that on our left hand side we're having 12 hydrogens. Then on this other hand we are only having 2. So now to balance that one, we're going to put a coefficient of 6. Then everything here now affects the number of oxygens that we are having there. So if we can see here, we're going to say our number of oxygens on our left is going to be 7 times 2, which is 14. Then this other one here is going to be 6, right? If we add 14 plus 6, we're going to get a value of what? Of 20. So for us to get a 20 there, we must balance with a coefficient of what? Of 10. So it's going to be 10O2. Then that's how we balance our what? Our equation. Now we're going to move on to question number 3 there. So 3.1 says here, what the relationship between boiling points? So we're looking at boiling points and the number of carbons, right? So the number of carbons, all of them, they are straight chain primary what alcohols is investigated. The following curve is obtained obtained then after this now we're going to say, they are saying there we are supposed to what? Says the graph of the boiling point versus the number of carbon atoms. Then having that now we're going to say the first question they're saying define the term boiling point, right? So we need to know what the boiling point is. So here take note is always start by the temperature. So if this keyword is not there, it means now your definition is going to be considered as wrong, right? So it's going to be the temperature at which vapor pressure, temperature at which vapor pressure of a substance, of a substance, of a substance. Let me just like maybe zoom in a little bit. Temperature of a substance equals atmospheric pressure equals atmospheric pressure, like that. So this is how we define our term boiling point, right? So then moving on there, they're saying 3.1.2, we are asked about what is the structural similarity between the alcohols that make this a fair investigation, right? So what makes it fair is that all of them, they we are told at the top, all of them they are primary alcohols, and they all have what? Straight chains. So straight chain and also what? Primary alcohol, right? So I'm going to start by saying primary alcohols. So I'm going to opt for primary alcohols, right? So if you want to proceed, also you can also identify them as being all having what? Straight chains there. Then 3.1.3 says which van der Waals forces is responsible for the trend observed in this curve, right? So they are looking for a van der Waals force that is present responsible for the trend observed in this curve, right? So in terms of this, they were going to say we have got our London forces there. So a London force is an example of a what? Of a van der Waals force. So it's London forces there. Then 3.1.4 says write down the IUPAC name. So we're looking for the IUPAC name of the alcohol with a boiling point of approximately 410 kelvins, right? So in terms of this there, let's look at the number of carbons there, right? So it means 410, right? So in approximately 410, right? So this is our 400 there. If you can look there, this is our 400. So above 410 there, it's going to be this here, which is now the number of carbons there. We're going to have what? 5 there. So it means now our IUPAC name is going to be pentane 1-ol, right? So it's going to be pentane 1-ol, right? So remember, these are all what? Primary alcohols, right? So I'm going to say pentane, then dash all, right? Pentane 1-ol there. So that's the IUPAC name that we're looking for, right? Then after that, they're saying another investigation is carried out to determine the effect of structural differences on boiling point, right? So they are looking at the structural differences of boiling point on the boiling points. The table below shows the different compounds and their respective molar masses, their respective molar mass that was used in this investigation, right? So it says here which compound A, B, or C will have the highest boiling point, right? So now we're having our compound there, then we're having the molar mass there, right? So in terms of this there, we should look at the type of the intermolecular forces generally. So our answer there, I'm going to go for option C. Then option C, we can see this is an acid, and then this one also is an alcohol, then this one is going to be what? A ketone, right? So in terms of this, is comparable there, but in terms of this one here, which is a butane, is going to have what? Butane is a ketone, so it's going to have dipole forces, dp forces, right? Then on this one here, which is our butane 1-ol, is an alcohol. What we are going to have there is hydrogen bonds. I'm going to just say H bonds, and then also propanic acid is going to have what? Hydrogen bonds. Then now we're asked to fully explain the answer in the answer to question 3.2.1, right? So allow me to use this other space there to explain that part there. So I prefer to write this in bullets, right? So we're going to start with compound A. So I'm going to say compound A, already I identified compound A as in says here is a butanon, so it's a ketone, therefore it has got what? The type of bond there is going to be dipole, right? Dipole forces, right? So compound A has dipole forces. I'm going to say dipole forces. Compound A has got dipole forces, right? So the next bullet there is going to be based on the other compound, right? So compound B, which is our alcohol there, compound B, I'm going to also identify his hydrogen bonds, right? So hydrogen bonds, right? So you can see I'm trying to identify the intermolecular forces, the type of these intermolecular forces, which causes what? The differences, right? Then I'm going to proceed again to our compound C there, which is R and a carboxylic acid. Yes, a carboxylic acid. Then I'm going to say compound C also has hydrogen bonds, right? So hydrogen bonds. Now the question might arise and say, okay, since these two have got the same type of bonds, why is it that C has got what? A higher boiling point than what? Than B. Now the reason behind then I'm going to say compound B there. I'm going to say compound B, compound B, which is an alcohol, has one side. I'm going to say one side for H bonds, right? For hydrogen bonds, right? Then on the other end, when it comes to compound C, compound C has, which is a carboxylic acid, has two sides for H bonds, right? For hydrogen bonds, right? So now what does that mean? It means more energy is going to be needed. More energy is needed to overcome intermolecular forces in, I'm going to say in C than in A, right? So that's how we attempt that question then moving forward to the next question there. So we're done with 3.3, 3.2.2, moving forward to question 4.1. So question 4.1 is there. Consider the three organic reactions 1, 2, and 3 below. There says option 1 there, we're having our pent 1 in there, which is your HCl, then organic compound P as the measure product, right? Then after that, they are saying here, reaction number 2, we have got organic compound P and plus sodium hydroxide to give us a secondary alcohol Q plus sodium chloride. Then organic reaction, which is reaction number 3, organic compound P plus sodium hydroxide, again compound R plus sodium chloride plus water, which is our measure product, right? So 4.1.1 says the is paint 1 in saturated or unsaturated, right? So give a reason for an answer. So you can see the paint 1 in is an alkene, right? So alkenes, they are unsaturated. So our answer there is going to be unsaturated, right? So they are unsaturated hydrocarbons generally because they contain carbon and hydrogen atoms only. So here I'm going to say the reason behind is that it contains a double bond, right? So it contains a double bond. I'm going to say double bond there between C carbon to carbon atoms in the hydrocarbon chain, like that. Okay, that's what you're having then. Then 4.1.2 says write down the type of reaction represented by reaction 2 there, right? So the type of reaction represented by this one there is going to be our substitution, right? So substitution, right? So for it to be easier, we can be specific if we want to be, but if it's not specific like this, so type of fraction is substitution, say you the substitution, right? So or else if you want to be specific there, we can refer to this one as hydrolysis. So it's going to be our hydrolysis like that. Then reaction 3, also we're looking for the reaction 3. So reaction 3 there, what do you have there? We're going to have what we refer to as elimination, right? So it's an elimination reaction there. So that's the type of reaction that we are having there. So if we are to be specific there, we refer it to as dehydrohalogenation, right? So going to be dehydrohalogenation, like that. So this is what you're having. Then now 4.1.3 under that they say write down the structural formula of compound P, right? They're looking for the structural formula of compound P. So the structural formula of compound P, so which is our P there, we started with it from the top until where we got to number 3 there. So compound P there is going to be our main carbon chain there. I'm going to say in terms of this, I'm going to have a 5 carbon chain. I'm going to use a 5 carbon chain. So I'm going to say 1, 2, 3, 4, and 5. Like that, right? Then after that, now I'm going to say a Cl there, which is our chlorine. Then after that, the rest are going to be what? Our hydrogens, like that. I'm going to add our hydrogens like that. Hydrogen, hydrogen, hydrogen going downwards like that, hydrogen, hydrogen, then hydrogen, and also another hydrogen like that, right? So this is how we identify our organic P there, right? Then moving on, they are saying here, why did I use a 5 carbon chain? If someone might ask, why did I use a 5 carbon chain? Because here we're told pent one in, right? So it's pent means how many carbons? 5 carbons. Then moving on to compound question 4.5, it says the IUPAC name of compound Q, right? So Q is a product on in reaction number 2, which is a what? Which is an alcohol, right? So now we're having this reactant there, which is our organic P, this organic P there. So if I can put maybe a circle around it so that you can see it. So it reacts there. What does it react with? It reacts with sodium hydroxide to formulate a secondary alcohol, right? So in terms of this, now we are asked in terms of the name of the secondary alcohol, right? The IUPAC name of the secondary alcohol. Take note, this is not going to change the number of carbons. It will remain the same, right? So it means now we're going to have pentane. For it to be a secondary alcohol, what do we need there? So it's going to be 2-ol like that. So our IUPAC name is going to be pentane 2-ol. Then moving on to 1.6 says here, reaction 2 and 3 require the use of a strong base. So we're using a strong base there, which is our sodium hydroxide there, P, which is our sodium hydroxide there, NaOH for reaction 2. And if you can also look at reaction 2 there, we also have a strong sodium hydroxide. So it's a hydroxide there. Sodium hydroxide is a example of a strong base. Then write down the conditions that will prefer the reaction 2 over write down the conditions that will prefer reaction 2 over reaction 3, right? So we're looking for the reaction conditions there. So instead of using a strong, we're going to use a dilute strong base, right? So we're going to use a dilute strong base like that. Okay, so this is our answer there. Dilute strong base. We're going to opt for a dilute strong base or sodium hydroxide in mild heat, or we can also go for sodium hydroxide, which is NOH, and mild heat, right? So mild heat. So this is how we attempt question 4.1.6. 4.17 says paint one in and organic compound are isomers, right? So what type of isomers is pent one in and organic compound are, right? So in terms of this, now we need to know the type of what of isomers between pent one in and our compound are, right? So if we're having that now, we're going to proceed and say these are going to be our positional isomers, right? So the correct answer there is going to be positional isomers, right? So these are positional isomers. Then moving on to 4.2 says the flow diagram below shows the conversion between butane 1-ol to butane gas, right? So this is a flow diagram, the flow diagram that we're having from butane 1-ol to step number 1, then organic compound X, then step number 2, we're having a butane, right? So the following chemicals are needed. So we're having concentrated H2SO4, then platinum PT, then H2, right? So using condensed structural formula, write down the balanced equation and indicate the chemicals used in each step in the preparation of butane gas from butane 1-ol, right? So preparation of this butane gas from butane 1-ol. So we're starting from there to the end here. What are we supposed to do? We're supposed to use the condensed structural formula, right? So in terms of this, I'm going to say butane 1-ol is going to be CH3, then our CH2, CH, again CH2, then CH, then after that I'm going to say CH2, butane, 1, 2, 3, 4. So it should be having how many carbons? 4 carbons, right? So it's going to be CH2, 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 which is carbon 1, 2, 3 there. Then I'm going to add another CH2. Then I'm going to say OH there, right? So because it was an alcohol, right? Then after that, now I'm going to say the what do we have there? We're given concentrated H2SO4, right? So over the arrow there, I'm going to say conc, then H2SO4, right? So what is it going to give us there? It's going to give us an organic compound X there. So our organic compound X, I'm going to say is CH3, 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 CH2, CH2, CH3, CH2, then CH again, CH, then I'm going to say what? CH2 at the end, right? So CH2, then CH2, then I'm going to say plus our water, which is our H2O, right? So H2O, right? So this is step number one or reaction number one, right? Then after that, now if I'm to proceed to the second step there, so second step there, I'm going to say again CH3, CH2, CH2, CH, CH, right? So you can see now we're using this part of the product, right? Then after that, I'm going to say CH2 again. Then after that, I'm going to add our hydrogen, right? So hydrogen there. Then now a catalyst there, PT is going to be used, right? So PT is going to be used. Then we're going to have a CH3, CH2, CH3, CH2, then CH2 again, CH2, then CH3. So CH3. So at the top there, if I can just like change color. So at the top there, we're going to have a reaction number one or step number one, right? Then at the bottom there, we're going to have our reaction number two. So these are the answers that we're having there. So now moving forward to the next one there, it says here, question 5 there, the reaction between excess hydrochloric acid, the reaction between excess hydrochloric acid. So HCl with zinc is used to investigate factors that influence the reaction, right? So we're looking at the factors that influence a reaction, right? So the balanced equation there, we're given something like this. This is Zn plus 2HCl to give us zinc chloride, then H2. Then the reaction there, it shows that it is an exothermic reaction, right? So now to proceed to the next question there, it reads here, it says 3 experiments are carried out. So 3 experiments are carried out and one factor is changed. So there is a change of a factor in the experiment. Then the same volume of hydrochloric acid and the same mass of zinc granules are used in each experiment. Then the hydrochloric acid completely covers the zinc in each of the experiment, right? Then after that, now they're saying the table below shows the reaction conditions, right? So experiment 1 to experiment number 3. Then let's look at the concentration there. So there, the concentration that's same. So it means here it has changed. Here copper, which is a solid present. No. Then here the other one is present, right? So now what us to define the term reaction rates, right? So this is the change in concentration of reactants or products. So it's going to be change in concentration. I'm going to say concentration, right? In of reactants, I can say of reactants or products. Reactants or products per unit time. Per unit time. So it's important for us to consult the exam guidelines when it comes to our definition of terms. Now, moving on to the next question there, it says here, write down an investigative question when comparing 1 and 2, right? So take note there, you should identify the independent and the dependent variables there, right? So basically, if I'm to write a basic there, I'm going to say, what is the relationship, okay, what is the relationship between the concentration and reaction rates right, like that. So now I was able to identify the what are the independent and the dependent variables. Then moving on to 5.3 says the KF not drawn to scale is obtained from the volume of hydrogen gas H2, then produced over time for experiment number one, right? So we're focusing on experiment number one at the top there. It says, how does the rate at which hydrogen gas is produced between T1 and T2? So it says, how does the rate at which hydrogen gas is produced between T1 to T2 compared to that of T2 to T3? T3, right? Write down only higher than or lower than or equal to, right? So in terms of this one, we're going to say higher than, right? So there we can see in terms of what 1 T1 and T2, right? So here we can see the graph is more steeper, so it means now the reaction rate is going to be faster. Then as it gets here, it means it's getting what this part here under T2 to T3. What is happening there? It becomes what slow as it's actually getting what using up the reactants then. So now it says 5.3.2 says redraw the graph in the answer book and clearly label the curve as A, right? So on the same set of axes, get the curve that will be obtained for experiment number three and label this curve B. So let's look at experiment number three. What was changed at experiment number three? So the concentration there again, and then what did we add there? We added more of copper, right? So if we added more of copper, so if you look there, they're saying we're adding more of what? Of copper. So in terms of this now, if we're adding more of copper, what is going to happen there? We're going to have like reaction B there. So we're going to have something that is more steeper there, then actually goes up and joins this other graph there. So this is going to be our graph B, and then this original one there, we're going to remain as what is our graph A. Then after that now, it says the reaction in experiment one takes 58 seconds. So we're given the time of the reaction, which is 58 seconds, to reach the completion, and the average reaction rate at which hydrochloric hydrogen gas H2 is produced is that. So we're given the reaction rate. So the reaction rate there is 8.39 cubic centimeters per second, right? Then after that, calculate the initial mass. So they're looking for the initial mass of zinc used in the experiment, right? Then they are also saying the molar volume of the hydrogen gas H2 at 25 degrees is 24,000 cubic centimeters per mole, right? Then experiment number four is now conducted by, okay, so experiment number four is now conducted by increasing the temperature of the reaction mixture in the experiment one, right? So now I think okay, so I think this question was supposed to end where calculate the initial mass of the zinc there, right? So I can say the 5 there, right? So let's start by calculating the initial mass of the zinc there, right? So in terms of this, I'm going to say rate the reaction rate, right? So in terms of this, I'm going to say our rate, which is our reaction rate there, is equivalent to change in volume, right? Change in volume all over change in what in time, right? So now someone might ask, why do I use that option there, right? Why did I go for that option there, right? So you can see there, what do we have in terms of our units of measurement? We're given cubic centimeters, then which is the top there, the volume, right? Then per second, which means is our time, right? Then now I'm going to say what we given there. Also, this is the amount of the rate that is produced there, the reaction rate, the average reaction rate is that value, which is 8.39. Therefore, I'm going to say 8.39 is equivalent to the V, right? So it means now the initial was what? So delta V means what? Final minus our initial. So it's V minus initial, which is 0 all over the change in time. So the change in time, they were told it takes 58 seconds. Therefore, I'm going to say all over 58 then. Then to proceed there, I'm supposed to calculate our V. So it means our V, I'm supposed to cross multiply, right? So if I cross multiply 8.39, so it's going to be 8.39 multiplied by 58, right? So 58 there. So our answer that we're going to get there is going to be 486.62, right? So it's 486.62. Then I'm going to say cubic centimeters, right? So this is what we are going to get then. Then after that, now I'm going to proceed and calculate the number of moles, right? So in terms of our number of moles there, I'm going to say N is equivalent to V all over Vm, right? So then I will proceed to say there the number of moles there is equivalent to the volume that we got there. I'm going to substitute it here, which is 486.62 all over the Vm, right? So now we're given there, it says the molar volume of hydrogen gas at this temperature is 24,000, right? So I'm going to use that 24,000 at the bottom divided by 24,000 there 24,000, not 24,000. So it's just like a 24,000 like that, right? So I'm going to say divided by 24,000, 24, 1, 2, 3, 1,000 is equivalent to, so I'm going to get a value of what? 0,00. Okay. So this gives me a value of what? Our n there is going to be 0,0 uh, 202, right? So I can leave it like that, 0,0202 moles, like that, right? Then after that, now I'm supposed to proceed to use the mole ratio. So the number of moles of hydrogen gas there, these are the number of moles of what? Of hydrogen gas, right? So maybe if I can just like be specific at the top there to say the number of moles of what? Of hydrogen there. This is what we're having, right? Then is equivalent to, then according to our balanced equation there at the top, we are going to, okay, it wasn't given, right? So in terms of the balanced equation, I can say the number of moles between this zinc and this hydrogen, right? So I'm going to say N of Zn there, right, is to the number of moles of what? The number of moles of, let me just like go back again there. Uh, Okay, so we're given there at the top, right? So if you can look at the number of moles of zinc, there is 1 is to 1 with what? With our hydrogen, right? So the mole ratio is going to be 1 is to 1 there. So that's what I was looking for. There, I'm going to say number of moles is to number of moles of what? Of hydrogen gas, like that, right? So we agree this one is going to be 1 is to 1, right? So what does that mean? It means here we calculated the number of moles for this one to be 0.020, and then this other one I can also proceed to say 0.020, right? So then to proceed there, it means these are going to be equal. Then after that, now I'm going to calculate the mass of this one, right? So the number of moles, remember, of zinc there is equivalent to the mass all over the molar mass, right? Then if I'm to make the mass the subject of the formula, I'm going to say the mass of what? Of zinc there is going to be what? Nm, right? So Nm, like that. Then after that, now I can proceed to substitute the n there, which is 0.020, then multiplied by the molar mass of zinc. So if you look at our periodic table there, you're going to get a value of what? Of 65. Then after that, now let's multiply there to get our m. So n of zinc there is equivalent to what? So let's multiply there. I'm going to say multiplied by 65, my answer there. So according to this one, I'm getting a value of what? 1,30. So it's going to be 1,30 grams, like that. So that's my final answer there. Then question 5.5, they're saying now experiment for is now conducted by increasing the temperature. So there was an increase in temperature of the reaction mixture in experiment number 1, right? So how will this change affect the reaction, right? So choose increase from increase, decrease, or remain the same. So our answer there is going to be what? Increase. So our correct answer is going to be increases, right? Then after that, explain the answer to 5.5 by referring to the collision theory, right? So now for us to be able to answer this one, we should understand the collision theory, right? So in terms of this, we know in terms of our temperature, temperature is the average what energy of the what of the kinetic energy of the particles, right? So it means here at higher temperature, I'm going to say it's high temperature. So in terms of 5.6, I'm going to say it's high temperature. Allow me to write my temperature like that. Allow at high temperature, the average kinetic energy, I'm going to say the average kinetic energy, I'm going to say EK again, of the particles is higher, of the particles is higher. So particles, they get what? Excited, right? So particles is higher. Skipped is there, is higher. So I'm going to say is higher. Then after that, now I'm going to proceed to say as my next bullet there. So this one is going to be my first bullet. Then the second bullet there, I'm going to say more particles have sufficient. So I'm going to say more particles have sufficient. More particles have sufficient. I'm going to say sufficient. So EK, which is our kinetic energy, I'm going to proceed to say for effective collisions, right? So for effective collisions, right? Then after that, or collisions, after that, now I'm going to say what is going to happen that, right? Because now more particles have got what? the higher the temperature, it means now these particles now are excited, right? So now what is going to happen there? So it means now we're going to get more effective collisions, collisions per unit time, per unit time. So this is what is going to happen in terms of that, right? So now we're done with our question 5.6. Now moving on to question number 6, which is our 6.1 there. Is they consider the following hypothetical reaction. So having A to give us the right R2P. So the data in the table below shows the equilibrium concentration of Ag and B at different temperatures, right? So temperature C, the temperature in degrees Celsius, 200, 300. Then for A, the concentration was 0.0125. Then for A, also at 300, 0.171. Then for B, we're also having that information. Then now the first question there, it says state Lee Chatlay's principle. So I'm going to say when the equilibrium I'm going to say when the equilibrium, I'll just write equilibrium in a closed system, so in a closed system is disturbed, is disturbed, what happens there? The system, I'm going to say the system will reinstate a new equilibrium, and then how does it do that there, right? By favoring the reaction the reaction that will oppose the disturbance, that will oppose the disturbance. So that's how we attempt that question there. We were supposed to state the Le principle. Then question 6.1.2 says, is the forward or reverse reaction favored at 200 degrees, right? So now in terms of our answer there, I'm going to say forward reaction. So our answer there is going to be forward reaction. Therefore, now why is that so? So the equilibrium concentration of B is higher than A. So the equilibrium, I'm going to say the equilibrium concentration of B, I'm going to say concentration of B is higher than A. Is higher than A, right? Then now it says here, how will the equilibrium concentration of A at 200 degrees be affected by the following, right? Then moving on to 6.1.3, they say choose from increased, decrease, or no effect, right? So the pressure is increased, right? So how will the equilibrium concentration of A at 200 degrees, right, be affected by the following? Choose from increased, decrease, or no effect, right? The pressure is increased, right? So it's going to increase there, right? So this one is going to be also what? Increased, right? Then addition of a suitable catalyst. Remember, a catalyst just like speed up the rate of what? Of reaction there, right? So no effect there. So just the reaction is going to be faster. Then they're asking us, is the forward reaction exothermic or endothermic, right? So if we're to look at that there, in terms of our temperature there, we're going to say our reaction is exothermic. So the type of reaction that we are having here is exothermic, right? Then after that, proceeding to the next question there, says use Le Chatelier's principle to refer to the data in the table to explain the answer to question 6.1.5 there, right? So now I'm going to explain that part there. So I'm going to say the concentration of A, I will start with the concentration of A. I'm going to say the conc for concentration of A. The concentration of A increased. The concentration of A increased, right? Then now, what is going to happen there? I'm going to say an increase in temperature, an increase in temperature. Okay, what does it favor? Favors an endothermic reaction. Favors an endothermic favors an endothermic reaction, endothermic reaction, right? So that's an increase in temperature favors an endothermic reaction, right? Then after that, the reverse reaction is going to be favored. The reverse, as the closing bullet, the reverse reaction is favored, is favored, like that. So now moving on to question 6.2 there, right? So 6.2 there. Question 6.2, it says there, initially 1,05 moles of bromine gas. So initially 1,5 moles of bromine gas, bromine there, which is Br2, are sealed in an empty container. The following reaction occurs at 1,600 degrees. Therefore, having Br2 gas, then reversible reaction, which is 2Br gas. Then at equilibrium, the concentration of Br2 is that value 2.074 mole per gm cube. Then the equilibrium constant Kc is 6,34 times 10 negative 4 at 1,600 degrees. Then now we're asked to calculate the volume of the container. So we're looking at for the volume of the container there. So for us to calculate the volume, so on this one, allow me to use this new page on this other end. So now we're going to start with our Kc expression. So our Kc expression, remember, is going to be Kc is equivalent to the concentration of our products. So in this case here, our products, these are our products, right? So which is 2PRG. So I'm going to say is equivalent to concentration of what? Product, which is 2Br. So I'm going to say Br there, Br, then after that, squared all over the concentration of our reactants, which is our Br2 there, right? So this is our Kc expression, Br2, like that. So this is how it looks like. Then after that, now I'm given already given a Kc value of what? 6,34, right? So I'm going to proceed and say the Kc is 6,34. So I'm going to say Kc is 6,34, right, times 10 exponent negative 4 there, right? Then is equivalent to, so now the concentration of those, right? So now I'm going to say is equivalent to the concentration of what? Br. We don't have, we're not given the concentration of this one. Therefore, I'm going to say squared all over the concentration of Br2, right? So let's look at the concentration of Br2 there. So it says here the equilibrium constant is that, and then at equilibrium, the concentration of bromine is 2,074, right? So I'm going to substitute that one there as 2,074, like that, right? So we're supposed to cross multiply to get the concentration of what? Of our Br there, right? So it means now if I cross multiply there, I'm going to get a value of what? Let's cross multiply there. Then I'm going to say Br 2.074, then multiplied by 6,34, 6,34, then times 10 exponent negative 4, like that, and close bracket there. So we're going to get a value of what? 0,0113, like that, right? So if we are to cross multiply there, that's what we are going to get is our Kc is the concentration of. So there, okay, it's squared there, remember. So if we do our math, they are going to get a value of 0,001 3131. I'll just write everything in full. 4916, right? 16 there. So take note also what we are looking for is Br, not Br squared. Therefore, we're supposed to say the root of that 0,00131 4916, right? So if we were to do our math there, we're going to get the concentration of Br as what? A value of it's going to give us 0,03626, then its concentration, right? So I'm going to say mole per dm cube, right? Then after getting that value there, we're now going to proceed to formulate some sort of a rise table, right? So I'm going to say there like that quickly. Then I'm going to draw something like this. Then let's have a table there. Therefore, here I'm going to say Br2, right? Bromine. And then here I'm going to say 2Br like that, right? So now this is what we're having is our table there. Then pardon my lines, they are not a bit straight there. So this is what we are having there, right? So my table is going to look like this, right? So now having that table, now I'm supposed to populate, or we are going to populate it with information, right? So I'm going to just say a ratio there, start with the ratio. Then I'm going to say initial concentration, initial shell, then I'll put square bracket to represents what concentration. Then here I'm going to say change in concentration again, change in concentration. Then here I'm going to say equilibrium, then concentration, like that, right? So now I will use a different color to populate the information there. So now in terms of this, we started with 0 on this other end. Then what we also know at equilibrium there, the concentration of our Br2 was a value of what? 2.074 according to the data that is given there. We can see we're given that value there, 2.074 mole per dm cube, right? So having that there, also now the ratio or initial concentration, sorry, was 0, but the ratio at the top there, the ratio there, we're going to say the ratio is 1:2, like that, right? So now in terms of our change in concentration there, we can see that we got a value of what? Of 0.036, right, is the concentration at what? At equilibrium for this Br2, right? So for these two or Br there, right? So it means now I'm going to plug that value there, which is 0.0363626, like that, right? So we started with this 0, then we added something, then we got this value. So it means now we added that same value, 0.03626, right? So having that now, I'm going to use the mole ratio for us to get this one there. So if I'm having this now, it means that the ratio between your Br and your Br2 there, I'm going to say Br2, which is your bromine, versus 2Br. So you can see the ratio there is 1:2, right? So it means here, if we're having 0.03626 on this other end there, we're going to have what? Half of it, right? So it means here 0.03626 versus this other one, right? So it means now, what are we going to do? We're supposed to divide it by 2, this value divided by 2. So if we divide it by 2, we're going to get a value of 0.01813, right? So I'm going to put that value here across, which is 0.01 813, right? So now in terms of this, remember what we asked there, we asked to calculate the volume of the container. So we're looking for the volume of the container, then we proceed there to say the initial concentration, right? So the initial concentration there, we're going to say what are we given in terms of our initial concentration. Let's look at our values there. If we're given the initial concentration of this there, right? So at the top there, if you can scroll there, so we're looking for the initial concentration, right? So the initial concentration there, we're going to say the initial concentration was a value of what? If I can just like go back there. So our initial concentration is going to be a value of, so here we're going to say what we're going to do here is to add these two, right? So to get this total there, we're going to add these two. Therefore, here I'm going to say proceed and say here, we're going to say 2.2.074. Then we're going to add that value of 0.01813, right? So if we were to do our math there, we're going to get a value of what? 2.09. So it's 2.09 213, right? Then after that, now we're going to take that same value, then plug it in here into this formula. So we're going to say our V is equivalent to, okay, so in terms of our concentration, how to calculate concentration, we're going to say concentration is equivalent to the number of moles all over the volume, right? So in terms of this now, I'm going to say the volume is to make the substitute formula. Therefore, I'm going to say your V is equivalent to N over C, right? N all over C. Then I will proceed to say there, what do we need there? I'm going to say V is equivalent to the number of moles that we already have there is going to be a value of what? The number of moles there is going to be a value of okay. So if we were to go back there, we given the number of moles there. So the number of moles there is going to be equivalent to a value of is going to be 1,05. So these are the initial moles of what? Of bromine there. So I'm going to take those number of moles as 1,05, then all over the concentration, right? So the concentration that I'm going to use there is the change in initial concentration, which is 2.09. So it's just 2.09, then 2.13, 2.13, right? So if we are to do our math there, we're going to get a value of what? 0,0,50, then the units of measurement there is going to be not in dm cubed. So that's how we attempt that question there, which is our 6.2, right? Now moving on to question 6.7.1 there. So 7.1 reads the sulfuric acid is a strong acid. So sulfuric acid is a strong acid, and that ionizes in two steps as represented by the equation below, right? So it ionizes in two steps, right? So now it says here, step number one, this is step number one is given, then step number two, then explain what is meant by a strong acid, right? So here is more of them asking us to define what a strong acid is. So I'm going to say a strong acid ionizes, a strong acid ionizes, so it ionizes completely. This one ionizes completely in water. In water, I'm going to say in water. Okay, so what does it produce there? To produce in water, to produce a high concentration, I'm going to say conc of H plus ion, of H3O plus ion, H3O plus ion, which are our hydronium what ions, right? So now they're saying give a reason why sulfuric acid is referred to as diprotic, right? So now it donates two protons. So it can donate two protons, right? So two protons, right? So I can just say H plus in brackets, then write down the conjugate base of what? H3O plus, right? So in terms of this, the H3O plus, the conjugate base of H3O plus is going to be our H2O there, right? So you can see this one is going to go with that one there. So our answer there for the first one there is going to be 7.13 is going to be our water, which is our H2O there, right? Then 7.14, it says write down the formula of the substance that can act as an ampholyte. So an ampholyte is a substance that can either act as a base or an acid. So during the ionization of sulfuric acid there, so in terms of this, we can see our ampholyte is going to be this here, which is our SO4 negative, right? So it can either act as an acid or a base. So I'm going to say HSO4, then a negative. Then to proceed there, they're saying sulfuric acid is a concentration of this. So we're given the concentration of the sulfuric acid, then we're asked to calculate the pH value for the complete ionization, right? So allow me to use again that other page. So now we're going to proceed and say, in terms of this, underline that one there. So we're asked to calculate the what? We're asked to calculate, it says here, calculate the pH of value after complete ionization, right? So now we're given that concentration of what? 0,1, right? So in terms of that, I'm going to say the concentration, remember, I'm going to say here H concentration, so H3O plus, I'm going to say H3O plus. So we're looking for this H3O plus in terms of this, right? So we're given the concentration there of this one is 2, right? Is 0,1, right? So I'm going to say multiplied by 2 because remember your sulfuric acid is what? A diprotic. So it means it can donate 2 protons. That's why I'm multiplying by 2 for those HR plus ion or H3O plus what ions, right? So if I do the multiplication there, it's going to give me a value of what? 0,2. Then I'm going to say dm cubed, like that, right? So this is what I'm going to have. Then after that, now I'm going to proceed to calculate my pH. So pH, remember, by formula is equivalent to the negative log concentration of what? H3O plus ions, right? Then to proceed, then I'm going to say your pH is equivalent to negative log, then the concentration that we are having there, take note of the bracket. Now I'm no longer going to use square brackets, then it is equivalent to, so if I punch that in my calculator, negative log 0.2 is giving me a value of what? 0.70. So that's our pH there. Take note also, it does not have what? Units of measurement. Then moving on to 7.2, there it says here 1.2 grams of anhydrous oxalic acid, which is H2C2O4, is dissolved in water to make a 50 cubic centimeter solution. Then we are asked to calculate the concentration of the oxalic acid H2C2O4, right? So now I'm going to say concentration is equivalent to, I'm going to opt for this formula, C is equivalent to M all over MV, right? All over MV, right? So it means now the concentration there that we're looking for, I'm going to say in terms of this, our C is equivalent to, so we're given the mass there. Let's look at the mass there. It says here the mass is 1,2, right? So I'm going to use that value there, 1,2. So I'm going to say 1,2, right? All over the mass of this oxalic acid, right? So if I'm to do this in terms of the molar mass of this, right? So the molar mass of this day, if you can check, is HC2, H2C2. So I'm going to say H2, H2C2O4, right? So that's our what's our oxalic acid, right? So if I'm to find the molar mass of this one there, I'm going to say this is equivalent to 1 times 2, because we've got 2 hydrogens, then plus your carbon there is 12 multiplied by 2, then I'm going to say plus your oxygen, which is 16 times 4, right? So if I do my math there, I'm going to get a value of what? Of 90, right? So it's going to be 90. Therefore, I'm going to take the molar mass there, which is our 90. The take note there is an M there. So it's going to be an M there. So it's an M there. So it's 90, then multiplied by the volume, right? So let's look at the volume that we're given there. So we're given a volume of 50 cubic centimeters, and then this one is supposed to convert to a dm cube by dividing by 1,000, right? So if we divide by 1,000 there, it's going to give me something like, I can just say 50 times 10 exponent negative 3, like that, right? So all over that, right? So if I punch that into my calculator, it gives me a value of what? 0.27, I'm going to say mole dm cubed, mole dm cubed, like that. So that's how we go about this one there. So now to proceed to the next question, which is 7,2,2. 7,2,2 says here, oh, before there's a statement. They're telling us learners dissolved S grams of sodium hydroxide. So sodium hydroxide, which is your NaOH, to make 2 dm cubed solution of sodium hydroxide, which is NaOH. They transfer 25 cubic centimeters of sodium hydroxide solution to a volumetric flask and added distilled water to make it a diluted 100 cubic centimeter solution, right? So this is what we started. These are the processes and the steps that were given there, right? So then after that, now they say they titrate 43.8 cubic centimeters of this diluted sodium hydroxide solution, and then sodium hydroxide solution against a 25 cubic centimeter oxalic acid, which is that one prepared in question 7.21 to reach the end point, right? So now we're given again the balanced equation for this one. Then after that, they're asking us to calculate the mass X in grams. So calculate the mass X in grams of sodium hydroxide that was used to make the 2 dm cubed solution, right? So in terms of this, now I'm going to say the number of moles there. I'm going to start with the number of moles, right? So number of moles, I'm going to say the number of moles of HC is going to be HC H2C 20404 is equivalent to, so remember our concentration is equivalent to, the number of moles all over the volume. So what I did here is to make the number of moles the separable formula. Therefore I'm going to say is equivalent to C times volume, right? Then after that, now the concentration there, we already calculated the concentration of this H2CO2 at the top there. So I'm going to say this is equivalent to, then I'm going to take that value there and substitute it 0.27, then multiplied by the volume there. So I'm going to check for the volume there. So we're given a volume of what there, let me check. So they transfer 25 cubic centimeters, right? So that cubic centimeters there is supposed to be converted, right, to dm cubed. So I'm going to multiply it by, so 25 there, I'm going to say 25, then multiplied by 10 exponent negative 3, right? So it's a matter of dividing, same as dividing by 1,000, right? So if I can say 0.27 multiplied by 25 times 10 exponent negative 3, it gives me a value of, okay, I'm getting a value of 6.75 times 10 negative 3, right? Negative 3. So these are my moles there, right? So I got the value of what? Of my moles, right? So now I'm going to use the mole ratio in terms of this one, right? So in terms of the number of moles of what? I'm going to say the number of moles of sodium hydroxide is to the number of moles of what? Is to the number of moles of n is to, let me check there. So what are we given in terms of this there? So it means is to HC2, right? So we can see the mole ratio is 1 is to 2 there, 1 is to 2, right? So I'm going to proceed to say there is to the number of moles of what? H2C2O 4, like that, right? So according to our balanced equation, there is 2 is to 1, right? So according to our calculations, again here we got a value of what? Of 6.75 times 10 negative 3. Therefore it means here on this other side, I'm going to say this one is going to be double, so it's 6.75 times 10 negative 3, like that, right? So this is what I'm going to get. Then after that, if I'm to do my math, there's 2 multiplied by that, then I'm going to get a value of what? 0.0135, 0.0135, right? So these are the moles now of what I can say of what? Sodium hydroxide there. So these are the moles that we're having there. So then after that, now if we were to go back again to the question, say calculate the mass in grams. So it means we're looking for the mass of the sodium hydroxide that was used to make what? 2 dm cubed what? Solution then. So I'm going to proceed and say there, what do I have now? Again, I'm going to say the concentration, right? So I'm going to say the concentration of what? Of sodium hydroxide there. Let me be specific. So the concentration, I'm going to say concentration of the sodium hydroxide there is equivalent to, concentration by formula is the number of moles all over the volume, right? So now I'm going to proceed to say the number of moles now I have then, which is 0.0135, then all over the volume there, right? So now the original volume that we can look at there, we're given a volume of what? They titrate 43.8 cubic centimeters of this, right? So I'm going to say all over 43.8, and then multiplied by 10 negative 3, like that, right? So if I do the math there, I'm going to get a value of what? So let me just quickly do this one is 0.0135, then divided by 43.8, which is multiplied by times 10 exponent negative 3, right? So according to my calculations there, I'm getting a value of what? 0, 0, 0, I'm getting a value of what? 0, this is equivalent 0.03. So 0.03, 0.3082, like that, right? So that's what I'm getting there, right? So then if I'm having that now, I'm going to proceed to say now, what do I have there? I'm going to use the titration formula, where I'm going to say C1 V1 is equivalent to C2 C2, V2, right? Like that, right? Then after that, now I'm going to proceed to say now, what do I have there? The concentration. So I'm going to say C1. This is the concentration I'm looking for. Then I'm going to use the volume, which is 25. So take note now, I'm not going to convert anything in terms of what? My volume, right? So now I'm going to proceed with the concentration of the what? Of the base there, which is our sodium hydroxide. So I'm going to say 0, 0. Okay, so I forgot there to put the units of measurement mole per tm cubed. So I'm going to say 0, 308. I can say 0, 308, then multiplied by the volume there, which is a value of what? Of 100, right? So I'm going to say 100. Then after that, now if I can calculate my C1 there, so I'm supposed to make the C1 separate formula. So it means now, what am I supposed to do? Basically, this is what is going to happen there. It means now I'm going to divide both sides by 25, then all over 25, like that, right? So this side is going to cancel. Therefore, to proceed with my C1 there, if I do the math now, I'm going to get C1 is equivalent to 0, 0.0308 multiplied by 100 divided by 25. So yeah, I'm getting a value of 1,232,232. Then I'm going to say the units of measurements are mole tm cubed, like that, right? So now to proceed there, I'm going to say now we have now the concentration of C1, right? So now what are we looking for? We're asked in terms of the mass, right? So now from the formula there that says C is equivalent to M all over MV, right? So what I'm going to do is to make M the subject of the formula. Therefore, I'm supposed to cross multiply there. I'm going to get something like this, right? So in terms of our values there, we now have the concentration. So I'm going to take the concentration there, 1,232, then multiplied by the molar mass there, which is equivalent to what? So if I do my math there, I'm going to get a value of what? Of 40. Then after that, multiplied by the volume, which is 2, because they asked us in terms of this, right? So it says here, calculate the mass x in grams of what? Of sodium hydroxide, right? So if you calculate the molar mass of this one, you're going to get a value of what? 40 there. Then after that, you're going to say 2 tm cubed there. So I'm going to say the volume is what? Is 2. So if I do the math there, I'm going to get a value of what? So I'm going to say 1,232 multiplied by 40, then multiplied by 2 there. So our final answer there is going to be 98,56 grams. So I'm going to get an answer of 98,56 then grams. Then we're done with that question then. Then moving on to the next question there, which is question number 8. Okay, question number 8 there says a standard electrochemical cell is set up as shown below. Then state the energy conversion that takes place in this cell, right? So now we're supposed to look at the type of cell. So here we're told it's a standard electrochemical cell, right? So in terms of this, now in terms of our energy conversions, now we're going to say is our chemical to what? To electrical, right? So it's easily identified by what? By that voltmeter there. So it's going to be chemical to electrical. So I'm going to say chemical to electrical, right? So electrical, like that. So that's how we answer that one. Then 8.2 says component Y ensures that the cell is complete, right? State one other function of the component Y, right? So take note of component Y. We refer it as a salt bridge, right? So the other one there, since we're given here, so the first reason there is there to complete what? The cell there. Then the other reason there is at this provide the path for movement of what? Ions, right? So it provides the path, the path for, I'm going to say movement of ions, right? So movement, there is an M of ions, right? So now they are asking us 8.3 there to write down the reduction half reaction, right? So the reduction half reaction there. So remember, a reduction, where does it take place? It takes place where reduction is, by definition, reduction is the gain of what? Of electrons, right? So now we're going to look at this one there. So our reduction half cell there, we're going to have our Fe, right? So this is our Fe there. So this is our Fe. Then after that, you're going to say our Fe in terms of our reduction there is going to be Fe 3 plus, then plus an electron, then to give us an arrow there of what? Fe2 plus, right? Fe2 plus, like that. So this is shows the what? The reduction half cell, right? Which is more of like the gain of what? Of electrons there, right? So you can see here, you started with a 3 plus, then you ended with what? A 2 plus. There it shows that there is a gain of what? Of electrons. Then we're moving on to say 8.4. It asks us to calculate the initial EMF of the cell, right? So for us to calculate the EMF of the cell, so we're going to employ the formula of E theta cell. So E theta cell is equivalent to E cathode, right? So E theta cathode. So take note, we are supposed to write this cathode in full. So if you say E cat and E n anode, there is going to be wrong. So your cathode should be written in full minus E theta of the what? Of the anode there. So this is what you're going to have, E anode there. So I'm going to say this one is going to be what? So now let's look at our values there. So I'm going to employ the reduction table there to check our values there. So now if we are to look at our values there for iron Fe, they were having this value of what? 0.77, right? So we're going to have a positive of 0.77, right? So now we know what is happening there, right? So it's 0.77, right? So according to this also, what did we say at the top there? So if you can look at this question there for question 8.3. So it means here is a reduction, right? So reduction happens where? At the cathode, right? So at the cathode. So this is going to be our cathode, and then this other one now is going to be our what? Our anode, right? So this one is going to be our anode. This side there, we're going to have our cathode there, right? Therefore, after that, now we're going to say, to proceed there, we're going to say your E theta cell is our cathode. So we got that value for iron there, which is our Fe is a value of what? A positive 0.77. So I'm going to say 0.77, 0.77, then minus there. Therefore, we're subtracting what? Our PV there, right? So if we were to look at the reduction table there, what are we going to find there? We're going to find our PV there. So let's find our PV. This is our PV there. So we can see it has got a value of what? Negative what? 13 there. So it's a negative 13 there. So I'm going to proceed to say there negative 13. So I'm going to say here minus. Then this negative is solved formula. Then I'm going to say negative 13 there. So I'm going to get a value of what? So also take note, your value should always be positive for an E theta value. So if you find your value being negative, just know something is wrong there. So our answer there is going to be a value of what? I'm getting an answer of okay, 0.77 plus 13 there. The value of what? 13 point E theta cell is equivalent to 0.77, 0.90. So I'm going to get a value of what? Oh, let me see something here. The E theta values there that I'm getting. Let me look at my E theta values. Negative 0.13, 0.13. Oh, okay. So it's 0.13. So I made a mistake here. It's supposed to be 0.13, not 13. Negative 0.13, like that. Okay, so now I'm going to proceed and add those two, right? So it's going to be 0.77 minus is going to give me a plus. Then I'm going to 0.13 there. So my answer is going to be a value of what? 0.9 volts, right? So I'm going to say 0.90 volts, right? So this is how we calculate our E theta cell. Then we proceed to 8.5. So 8.5 is there. How will the reading on the voltmeter be affected if then choose from increases, decreases, or remains the same if the initial concentration of PV is increased, right? So if we increase the initial concentration of PV there, what is going to happen is that our concentration, the reading on the voltmeter, how is it going to be affected there? Is going to decrease. So our first option there is going to be to decrease there. If we increase the concentration of what? Of PV there, our voltmeter reading is going to be decreased. Right then 8.5.2 says surface area of PT electrode is increased, right? So if we increase that one there, this one is going to what? Remain the same. Remember, remain the same. Remember, your PT there is innate, right? So it's just used to as an electrode so that it can conduct that electricity there. Then after that, it says here 8.5.3, the PB and PB2 plus half cell is replaced with what? With zinc there. Then explain the answer to question 8.5.3 by referring to the relative strength of the reducing agents, right? So to explain this one there, I'm going to say zinc and zinc and what is stronger? Okay, 8,6, 8,6. So we're replacing it with zinc with what? PB. So I'm going to have zinc and PB there, right? So zinc and PB. So let's look at our zinc. Let's look at the zinc there. Zinc Zn, Zn, Zn. So now this is our Zn there, right? So then to conclude this one, they were going to look at the oxidizing agent or reducing what agent, right? So now it says here going down there, it says increasing, reducing what ability. So now it means now our zinc is a stronger reducing what agent, right? So I'm going to say here is a reason there. I'm going to say zinc is a stronger reducing reducing agent, right? So it's going to be a stronger reducing agent than your PB, right? Than PB, right? Then after that, more energy. I'm going to say more energy per unit charge, unit charge, per unit charge is released for the reaction, for the reaction, for the reaction between zinc and Fe. Zinc and Fe 3 plus, right? So now as a conclusion that the equilibrium is going to lie to the right now. Our equilibrium is going to lie towards what? The right. Then now moving on to the next question there. So our next question is question number 9. It says a few drops of phenolphthalein are added to the concentrated sodium chloride, which is your NaCl solution. Then the solution remains colorless. Then the carbon electrons P and Q that are connected to a battery is dipped into the solution as shown below there, right? Then after that, now they're asking us to define electrolysis, right? So electrolysis there is defined as the chemical process in which, so I'm going to say electrolysis is the chemical process in which in which electrical energy is converted is converted to, let's say D there, to chemical energy. So it's a more of like stating the energy conversion is from electrical to what? To chemical energy. Then they're asking us to write down the name of the component that shows that the above cell is an electrolytic cell, right? What is it that shows that this one is an electrolytic cell there? We're given what? A battery there. So I'm going to say this is a battery, right? So a battery or a number of cells. So if you join more cells, we're formulating what? A battery. The 9.3 says write down the name or formula of the gas produced at electrode Q there, right? So in terms of this, what we're going to have there, we're going to formulate a hydrogen gas, right? So I'm going to say H2 gas, hydrogen gas, right? So I'm just going to say H2 gas there. Then after that, now write down the half fraction that occurs on electrode P, right? So at electrode Q there, we're going to have all those bubbles and stuff, right? Then after that, now we're going to say here 9.4, what is it that is going to happen there at electrode Q, right? So at electrode P, there we're going to say write down the half fraction that occurs on electrode P P, right? So in terms of P, they were going to focus on our chlorine, right? So remember, chlorine is Cl2, so it's diatomic there. For it means here, I'm not just going to write a Cl, right? So I'm going to say 2Cl there. Then I'm going to say this one is a negative. Then in an aqueous state, there is going to give us a Cl2 gas there. It's going to be Cl2, which is a gas, right? So then after that, plus how many electrons? I'm going to say plus 2 electrons like that. So this is what you're going to have there. Then they are saying 9.5 there. Phenolphthalein is colorless in an acidic solution and pink in an alkaline solution, right? Then write down the color of the solution around the electrode Q and the formula of the substance responsible for the color. So the color of the solution around our electrode Q there, and then write down the one that is uh, write down the color. Okay, so write down the color of the solution around electrode Q and the formula of the substance responsible for the color, right? So now our color there is going to be a pink right there. Then after that, now our reason behind there is because what we have there, we have our hydroxide ions that emanate from what? From sodium hydroxide, right? So I'm going to say OH what? Negative there, right? So that's the reason why we're having our color as being what? Pink there. Then 9.6 is there. An electrolytic cell is set up for the purification of copper. So we are purifying copper or that contains zinc and platinum PT impurities. Then after the purification of the impure, after the purification of the impure copper was completed, 1,38 times 10 negative 2 mole of electrons were transferred. Then the initial mass of the cathode is what? 2 grams there. Which metal besides copper will be oxidized there, right? Choose from zinc or platinum, right? So which one is going to be oxidized there? So it's going to be our zinc, right? So it's undergoing oxidation, right? So it is going to be oxidized. Therefore, it means here, then to proceed there, it says calculate the mass of the cathode after the purification, right? So in terms of this now, we're going to say the number of copper. So I'm going to say start with the number of what? Of moles, right? So the number of moles there of Cu, right, which is our copper. I'm going to say the number of moles of our copper is equivalent to the half, right? So half there of what? I'm going to say half of 1,38, or half multiplied by 1,38, then multiplied by 10 negative 2, right? 10 negative 2, right? Then after that, now we're going to say, if we're having that there, we're going to get the number of moles of copper as being what? A value of what? So if I say half of this, I'm going to get a value of what? So it's more of like 1,1,38 times 10 exponent negative 2, like that. Then we divide it by 2 there, right, which is a half. So I'm going to get a value of what? 0,069, right? So it's equivalent to 0,0069 moles, like that, right? So this is what we're having. Then after that, remember I asked in terms of the mass. So I'm going to say your number of moles is equivalent to the mass all over the molar mass. But now automatically after writing that formula, I'm going to make M the separable formula, which is equivalent to N times M, right? So after that, now I'm going to substitute with the values that we have there. So I'm going to say the mass there is a value of what? The number of moles we calculated there is 0,0069 multiplied by the molar mass, right? So the molar mass there is going to be 63,5, right? So if we multiply there, I'm just going to say for my answer multiplied by 65 there. So it gives me a value of 0,44, 0,44 85. 85, right? So this is what I'm getting there. I'm going to say this in grams, right? So now to proceed there, since we are saying the mass of the cathode after the purification, right? So I'm going to say there, we started with our M there, which is equivalent to the mass of the cathode there is equivalent to 2 plus. So there, remember we're given 2 grams there, right? So I'm going to say 2 plus, therefore 2 plus what? I'm going to say 2 plus 0, comma. So it's going to be 2 plus 0, comma 438, 438, 4, 4, 8, 5, right? So it means our M there is equivalent to a value of what? So if I add there, I'm going to add plus 2 is equivalent to, so it gives me a value of 2,44, right? It's going to be 2,44, 2,44, I can say 85 grams, right? So that's how we calculate the final answer there. So with that being said, thank you for watching.